It says use the properties of integrals to evaluate each of the following, and then these are the properties that we learned about yesterday. All right, so first one is telling you, okay, what's the integral from b to a of g of x? Well, if you look up here, you don't have the integral from b to a, you got the integral from a to b. All right, so we learned yesterday that these are reverse integrals of each other, so their values are going to be reversed. Okay, that's this property. Let's see, b to a to b, right here. Okay, a to b, and then b to a. Looks like it's missing a negative sign, so add that to that. There's no negative sign on that, and there should be. So you might want to do the same thing on this one here. There should be a negative there. Or actually, the negative goes in front of this one. My bad, guys. I'm sorry. So get rid of that negative. The negative should be here. So when we switch the upper and lower bound, then the sign or the value of the integral is going to switch. Okay, and we showed an example of that yesterday on GeoGebra. All right, so I know that this is going to equal the opposite of this. So this would end up equaling the opposite of negative 3, which would be 3. Okay. Then the next property we learned about was called the scaling property. So I'm taking this integral and I'm scaling it by 2. So that's just going to take the answer to the integral and multiply it by 2. So when you have a constant scalar, a factor that's a constant, okay, we can pull that out and then do the derivative, or do the integral. So in this case, the integral from a to b of f of x is equal to 8. So this is simply going to be 2 times 8. That integral is going to be 16. So it's doubling the area. So all that means is this, guys. If you took this paper that I gave you right here, okay, take a piece of tracing paper, just to demonstrate what's happening on that graph. Okay. All right. When this is, let's just say this is the function f of x for this example here. Okay. All right. So if you took f of x and you doubled it, do you remember from last year when the 2 is on the outside of the function, what that does is it takes all the y coordinates and it doubles it. It was called a vertical stretch. So if I was graphing the f of 2x to compare it to f of x, then I would take each one of the y coordinates and double it. Okay, so I just said let this area, in this case, let this area be 8, even though it's not 8 boxes. Just say this is 8. All right. If you take the previous y coordinates, so I just used the function the square root of x. So the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So this is 1, this is 2, this is 3. if we did this to the function, what it's going to do is just vertically stretch it. So each y coordinate is going to get multiplied by 2. So the 0, 0 doesn't move. Okay, the 1, 1 would now become 1, 2. Okay, the 4, 2 would now become 4, 4. And the 9, 3 would now become 9, 6. So if I graph those, okay, the 4 or the 2 becomes a 4, so it moves up to there, and then the 9 becomes a 6, so it kind of moves up to about there, and then my graph would look like this compared to the original. All right, and you can see that the integral, this distance right there, is equal to what it was there, so it's just been doubled. So now if this was 8, that's another 8, and the whole thing is now 16. Okay, so that's what's going on when you do this. That's just a vertical stretch. Okay. All right. What's the area, or what's the integral of a constant? Okay, so we did this yesterday. Okay, so if you had a constant, let's say 5, 1, 2, 3, 4, 5. So that graph would look like this. Right? If I wanted to find the integral between 2 points, A and B, let's say, so let's just say 6 and 10, and I wanted to find what's the integral of between 6 and 10 of 5 dx. Well, this is the function f of x equals 5. So our properties of, you could go through and do the antiderivative of this, which would be 5x to the first over 1, or just 5x. And then you could evaluate it from 6 to 10, right? So that would be 5 times 10, 50. Okay, take away 5 times 6, 30. So the area of that would be 20. Okay, that's using the fundamental theorem of calculus. However, we can see that this height is 5. This length right here is 4. So 5 times 4 gives you 20. So we said yesterday that when you have a constant, if I'm finding the area of a constant, or the integral of a constant, then I can get the width of the interval by subtracting the two bounds, b minus a, 4, and multiplying it by the height of the rectangle, which is going to be whatever the constant is, in this case, 5. So if I took the constant and then I multiplied it by the difference of the upper and lower bound, I get the area. Okay, because it's simply just a rectangle. So that's what's happening on this problem right here. So this would equal, okay, the height of the rectangle that's formed by this would be 5, and the width of the rectangle would be the difference of these two values, a or b minus a. This is the height of the rectangle. And this is the width of the rectangle. So that's my integral for a constant. Okay, so on D it says take the integral of 5 plus g of x. So we have two properties we can use here. One is the addition property, which means I can break this up into two integrals. So I can rewrite this by the addition property as the integral of 5 from a to b plus the integral from a to b of g of x. So what I'm doing right there is I'm using this addition property right here. I can just break it up into two. If it was a subtraction, I could break it up into a series of individual integrals and subtract them. Okay, well, we already did this integral. Okay, this was 5 times b minus c. We did that in example C. And then the integral from a to b of g of x is -3. So my overall integral would be 5 times b minus c minus 3. Not b minus c, b minus a, sorry. Okay, for part E, now you're yes? Yeah, go ahead. On part E now you would have, it's simply just the subtraction of those two integrals. So I can rewrite that as a to b f of x dx minus the integral from a to b of h of x dx. And then just pull the integrals for each one of those. So the integral of f of x is equal to 8. The integral of h of x is 5/2. And then I just subtract those two. So common denominator 2. Alright, so I'd have 16 and 5, so that's going to equal to 11 over 2. All right, then the last one was, we called it the breakup property. All right, so for example on this, if we had a graph and we had A, B, and then h of s at x was some graph above it, okay, and we shaded in the area here. Okay, that's the integral. Okay, so what this property said was, if you have an integral, you can rewrite, this is basically just rewriting an integral as the sum of two integrals. Okay, so if we said 4 is, if you knew that 4 is smaller than b but greater than a, then 4 is going to be between these 2 points somewhere. So I'm just going to say 4 is right there. So what this property says is, if you took the integral from a to 4, that would be this part, and then you added the integral from 4 to b, okay, that would be this part, then the sum of those two integrals would equal the integral from a to b. So this right here equals the integral starting at a and ending at b of h of x dx, and that would be equal to 5/2. And that's your integral. Okay, any questions on those 6 problems right there? All right, so go to this sheet that I gave you right here, and we want to figure out what these different integrals are. All right, so you're told that h of x, the integral of h of x between 7 and 9 is 4. So the area here is 4. Okay, don't do it by counting the boxes, just this area is 4. All right, so what would the integral be of 2h of x? 8. So our rule says that's 8. This is the scaling property. I can pull that 2 out, then do the integral of h of x dx, and I know that that integral has a value of 4, so that area is 8. Okay, and we demonstrated that using the tracing paper. Okay, now we're going to come back to these two here in a minute. Let's go down to the bottom one. What would the integral be of from 7 to 9 of h of x plus 4? So what's our integral on that one? Right. So this would be the same as the integral that we got. Okay, plus the integral from 9 to 7 of 4. So we know that this part is equal to 4, and we know that this part is equal to 4 times the difference of those two. This is the height of this rectangle, this is the width. So then altogether we'd have 4 plus 8, which that has a value of 12. That would be the area under the curve. Okay. All right, now let's take your graph, okay, and you're going to copy it. Okay, now let's just demonstrate what this thing looks like geometrically. What does h of x plus 4 do to this graph? When you take h and you add 4 outside the graph, what does it do to the graph? Okay, remember, this vertically stretched the graph by a factor of 2. So each y coordinate, we took it and multiplied it by 2. What does this do? Does what? Okay, so if you took this integral right here and you moved it up 4 spots, so here, 1, 2, this is 3, this is 4. The new integral for what you're figuring out right now, just take this, 1, 2, 3, 4. Okay, the new integral would look like that. But it would extend, the new integral would be this entire thing. Would be that part, plus this part, plus this part. That's the 12 that we get. The area under that now is 12, whereas it used to be 4. So this problem that we just did here is the same thing as taking this graph, sliding it up 4 places, and redrawing the rectangle. That's the new area that you're calculating. So you can see it's not double anymore like the last one, it's more than doubled. Okay, when we did this one, that area there just doubled to that area, so we got 16. All right. Now this was a different problem. The area here was 8. It wasn't 4 like it is on this one. All right. Okay, now take another sheet, trace it again. Okay, so do that. Okay. All right, now let's look at this one here. The second one. It says, what's the integral from 3 to 5 of hx plus 4? Well, we know the integral of h of x from 9 to 7. But now it's asking for the integral from 3 to 5 of h of x plus 4. So how could we use this to get this integral who's got different boundaries? Now the boundaries are 5 to 3. And it has to do with understanding what this does to h of x. So last year we did transformations. When you had a graph and it did this, that means it slid up. We took that graph and we slid it 4 up. If we did this, we slid it 4 down. Okay, if we did this, we vertically stretched it. Okay, if we did this, what did that do? Yes?
In that problem, isn't the +4 inside parentheses?
Yes.
Does the switch still count?
Does this?
Or you have to go left instead of right?
Correct. So this would slide the graph. Remember we called it Bizarro World? This has to slide 4 left. If it was h minus 4, that would slide the graph 4 to the right. So everything slides. The axes slide, everything slides. Okay, so now, if I took this and I slid it 4 to the left, ignore the original graph now. So I'm going to go 1, 2, 3, 4. That's your new graph. Okay, now the graph starts over here at -4. So what's the area from 3 to 5?
4.
Yeah. See, it didn't change because you just slid the entire graph. Okay, so when I slide it, everything slides. The upper and the lower bound slide as well. So when you take a graph and you slide it right or left, okay, and we slid the upper and the lower bound the same amount, then it doesn't change. It doesn't change the area of the graph. Okay, so this right here is going to be equal to the exact same thing. It's still going to be equal to 4. And so that's why I wanted to show it to you. So, because just describing it is kind of hard to see. So that would be, it's still going to be 4 if I slid it 4 places. All right. What would be another one that would equal 4? Let's say I said h of x minus 4 dx. What would we have to put in for the upper and the lower bounds here? So it would, say it again? Yeah, so now it would be the same as moving this 1, 2, 3, 4. It would now look like that, and this point would be 11, and this point would be 13. Still the same area. So if I gave you that problem, 11 and 13, that's also equal to 4. So as long as you're moving these bounds the same distance as whatever this is, then the area isn't going to change under the curve. All right, so let's say you had this. F of h of x minus or plus 7. And I told you this was equal to 4 as well. What would the new boundaries have to be? They used to be 9 and 7. Yeah, So now my original, this was 7. This moved 7 to the left. So that 7 became 0. This moved 7 to the left. So that became 2. That would also equal 4. Okay. 9 minus 7. 7 minus 2. So on this one, this was 9 minus 5, or 9 minus 4, and this one was 7 minus 4. So the area doesn't change. Okay, how about the last one now? The area from 3 to 5 of 2x plus the quantity h of x plus 4. 8, yep, I can factor out that 2, put it in front of the integral. From the previous problem, we established the value of this integral as being 4, so this just becomes 2 times 4, which is equal to 8. Okay. All right, so that finishes up the